transition from 3-prong to 4-prong appliance cords was driven by safety concerns and electrical code updates. The 4-prong circuit offers several enhanced safety features compared to the 3-prong system. The 4-prong circuit provides an insulated neutral conductor, a white wire, in addition to the insulated ground wire, green or bare copper. This ensures that the neutral wire is not used as a makeshift ground path. The insulated ground conductor, green or bare copper, provides a dedicated path for fault current to flow back to the service panel. This eliminates the risk of electrical shock if the appliance frame becomes electrified. In a 3-prong system, the neutral terminal can be connected to the metal frame of the appliance to serve as a ground path. This practice is unreliable for 2 reasons. Firstly, the neutral strap may be disconnected or loose over time, creating a potential shock hazard. Secondly, if the neutral wire becomes overloaded or damaged, it can carry current that was intended to flow through the ground wire, exposing the user to shock. The most critical scenario involving an appliance becoming electrified is when the appliance frame comes into contact with a live wire. This can occur due to damaged wiring or a malfunctioning appliance. In this scenario, a person touching the electrified frame could receive a shock because the current would flow through their body to ground. The severity of the shock depends on the amount of current flowing through the body. In extreme cases, severe shocks can cause electrocution. The transition to 4-prong appliance cords is a significant safety improvement that eliminates the potential for shock hazards associated with 3-prong systems. The insulated neutral and ground conductors provide reliable paths for fault current to flow back to the service panel, protecting users from electrical accidents. When electricity flows in a circuit, it needs a path to get to the device and a path to return. In North American electrical systems, we typically use 120 volts alternating current or 240 volts alternating current for residential applications. The 120 volts is often used for lighting and small appliances, while 240 volts is used for larger appliances like electric ranges and dryers. The current flows from the electrical panel through a hot wire to the appliance. The current then returns to the electrical panel through the neutral wire. The ground wire provides a safety path for current to flow in case of a fault. In a properly wired system, the ground wire should not carry any current under normal conditions. If a hot wire comes into contact with the metal frame of an appliance, the ground wire provides a low resistance path for the current to flow back to the electrical panel, tripping the circuit breaker and cutting off the power. This prevents the metal frame of the appliance from becoming energized, which could cause an electric shock. The 3-prong system, which was common in older homes, combined the neutral and ground functions. In this system, the neutral wire was connected to the metal frame of the appliance. If there was a fault, the current could flow through the neutral wire and the metal frame, potentially causing the frame to become energized if the neutral wire was not properly connected or if it became overloaded. The 4-prong system separates the neutral and ground functions, providing a dedicated ground wire. This eliminates the risk of the metal frame becoming energized in the event of a fault. The 4-prong system is now required by electrical codes for new construction and appliance installations. When installing a 4-prong cord on an appliance, it is important to follow the manufacturer's instructions and the electrical code. The ground wire should be securely connected to the appliance frame and to the ground terminal in the electrical outlet. The neutral wire should be connected to the neutral terminal in the outlet. The hot wire should be connected to the hot terminals in the outlet. If you are not comfortable working with electricity, it is best to hire a qualified electrician to install the 4-prong cord. When working with electricity, it is important to take precautions to avoid electric shock. Always turn off the power to the circuit before working on it. Use insulated tools and wear rubber gloves and shoes. Never work on electrical equipment when you are wet or standing in water. If you experience an electric shock, seek medical attention immediately. Electrical safety is an important issue that should be taken seriously. By understanding the basics of electrical systems and taking precautions when working with electricity, you can help to prevent electric shock and other electrical hazards. The National Electrical Code, or NEC, is a set of standards for safe electrical installation. The NEC is updated every 3 years, and it is important to stay up to date on the latest changes. The NEC covers a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. The NEC is not law, but it is widely adopted by state and local governments. Many jurisdictions require electrical installations to comply with the NEC. The NEC is a valuable resource for electricians, contractors, and homeowners. It provides guidance on how to install electrical systems safely and correctly. The NEC can be purchased from the National Fire Protection Association, or NFPA. The NFPA also offers training courses on the NEC. Understanding basic electrical concepts is essential for anyone working with electrical systems. Voltage is the electrical potential difference between 2 points in a circuit. It is measured in volts. Current is the flow of electrical charge through a circuit. It is measured in amps. Resistance is the opposition to the flow of current in a circuit. It is measured in ohms. Ohm's law states that voltage is equal to current times resistance, or volts equals amps times ohms. This law can be used to calculate the voltage, current, or resistance in a circuit if the other two values are known. Power is the rate at which electrical energy is transferred. It is measured in watts. Power is equal to voltage times current, or watts equals volts times amps. Understanding these basic electrical concepts can help you to troubleshoot electrical problems and to install electrical systems safely and correctly. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. An overload occurs when too much current flows through a circuit. This can happen if too many appliances are plugged into a circuit or if an appliance malfunctions. A short circuit occurs when a hot wire comes into contact with a neutral wire or a ground wire. This creates a low resistance path for current to flow, which can cause a large amount of current to flow very quickly. Overcurrent protection devices are designed to trip or blow when the current exceeds a certain level. This cuts off the power to the circuit, preventing damage to the wiring and appliances. Circuit breakers are resettable devices that can be tripped and reset. Fuses are one-time use devices that must be replaced when they blow. The size of the overcurrent protection device should be matched to the ampacity of the circuit wiring. The ampacity of a wire is the maximum amount of current that it can safely carry. The NEC provides tables that list the ampacity of different types of wires. Grounding is an important safety measure that helps to protect people from electric shock. Grounding provides a low resistance path for current to flow back to the electrical panel in the event of a fault. This helps to trip the circuit breaker or blow the fuse, cutting off the power to the circuit. Grounding also helps to prevent the buildup of static electricity, which can be a fire hazard. All electrical equipment should be properly grounded. This includes appliances, lighting fixtures, and electrical panels. Grounding can be achieved by connecting the metal frame of the equipment to a grounding electrode, such as a ground rod or a metal water pipe. Electrical safety is an important issue that should be taken seriously. By understanding the basics of electrical systems and taking precautions when working with electricity, you can help to prevent electric shock and other electrical hazards. Remember to always turn off the power to the circuit before working on it. Use insulated tools and wear rubber gloves and shoes. Never work on electrical equipment when you are wet or standing in water. If you experience an electric shock, seek medical attention immediately. The transition from 3-prong to 4-prong appliance codes is a good example of how electrical codes and safety standards evolve over time to improve safety and reduce the risk of electrical hazards. By understanding the reasons behind these changes, you can ensure that your electrical systems are up to date and safe. Consider the purpose of each wire within the 4-prong system. Firstly, the two hot wires, typically black and red, carry the 240 volts power to operate the appliance's heating elements. Secondly, the neutral wire, white, provides the return path for the 120 volt circuits used for the appliance's controls, timers, and lights. Thirdly, the ground wire, green or bare copper, is a dedicated safety conductor that provides a low resistance path for fault current to return to the electrical panel, tripping the breaker and preventing the electrical shock. The older three-prong system lacked this dedicated ground wire, instead relying on the neutral wire to also serve as the ground. This created a potential hazard because if the neutral connection became loose or broken, the appliance's metal chassis could become energized, posing a shock risk. The four-prong system eliminates this risk by providing a separate, dedicated ground wire. When retrofitting an older appliance with a four-prong cord, it's crucial to disconnect the bonding jumper that connects the neutral terminal to the appliance chassis. This jumper is only necessary in a three-prong system with the neutral is also used as the ground. Leaving the jumper in place in a four-prong system can create a parallel path for neutral current to flow through the ground wire, which is undesirable and can cause nuisance tripping of the circuit breaker or ground fault circuit interrupter, or GFCI. The potential for a shock is significantly reduced with the four-prong system because the ground wire provides a safe path for fault current to flow back to the electrical panel, tripping the breaker quickly and preventing the appliance's chassis from becoming energized. In a three-prong system, if the neutral connection is lost and a fault occurs, the appliance chassis can become energized, and anyone touching the appliance could experience a potentially lethal electric shock. The four-prong system is a significant safety improvement that eliminates this risk. The National Electrical Code, specifically Section 250.140, addresses the use of the grounded circuit conductor for grounding equipment. This section outlines the conditions under which it is permissible to use the neutral conductor for grounding non-current carrying metal parts of equipment. However, it also emphasizes the importance of a separate equipment grounding conductor for certain types of equipment, including ranges and dryers. The transition to four-prong receptacles and cords for these appliances is directly related to the requirements outlined in this section of the NEC. The code requires a separate equipment grounding conductor to minimize the risk of electric shock and ensure a safer electrical system. When examining electrical systems, it is crucial to understand the concepts of series and parallel circuits. In a series circuit, the current flows through each component in a single path. If one component fails, the entire circuit is interrupted. In a parallel circuit, the current has multiple paths to flow. If one component fails, the other components continue to operate. Most household electrical circuits are wired in parallel. This allows individual appliances and lights to be turned on and off without affecting the other devices on the circuit. The ampacity of a conductor is the maximum amount of current that it can safely carry without overheating. The ampacity of a conductor is determined by its size, material, and insulation type. The NEC provides tables that list the ampacity of different types of conductors. It is important to use conductors with the appropriate ampacity for the circuit to prevent overheating and potential fire hazards. Voltage drop is the decrease in voltage that occurs along a conductor due to the resistance of the conductor. Voltage drop can cause appliances to operate inefficiently or not at all. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. To minimize voltage drop, use conductors with a larger diameter or shorten the length of the circuit. Ground fault circuit interrupters, or GFCIs, are devices that protect against electric shock by detecting ground faults. A ground fault occurs when current flows through an unintended path to ground, such as through a person's body. GFCIs are designed to trip quickly when a ground fault is detected, cutting off the power to the circuit and preventing electric shock. GFCIs are required in wet locations, such as bathrooms, kitchens, and outdoor outlets. Arc fault circuit interrupters, or SIs, are devices that protect against fires caused by arc faults. An arc fault occurs when electricity jumps between two conductors, creating a spark. SIs are designed to detect arc faults and trip the circuit breaker, preventing a fire. SIs are required in many locations throughout the home, including bedrooms, living rooms, and dining rooms. Surge protectors are devices that protect electronic equipment from voltage surges. A voltage surge is a sudden increase in voltage that can damage sensitive electronic components. Surge protectors work by diverting excess voltage to ground, protecting the equipment from damage. Surge protectors are recommended for computers, televisions, and other electronic devices. When troubleshooting electrical problems, it is important to follow a systematic approach. Firstly, start by identifying the problem. What is not working correctly? Secondly, gather information. Are there any tripped circuit breakers or blown fuses? Thirdly, inspect the wiring and connections. Are there any loose or damaged wires? Fourthly, use a multimeter to test for voltage and continuity. Fifthly, consult the wiring diagram for the circuit. By following these steps, you can effectively diagnose and repair electrical problems. Remember to always prioritize safety when working with electricity. If you are not comfortable working on electrical systems, it is best to hire a qualified electrician. Electricians have the training and experience to safely and effectively diagnose and repair electrical problems.